Welcome everybody to this episode on dynamic programming. Today we are going to be talking about DPV 6.24, and 6.24 deals with the complexity, space complexity, mostly on the edit distance problem. And um, before we dive into the actual solution, the part one we just kind of set the stage, and we're going to be talking about how this problem is actually tackled in the book, because the problem actually refers to a solution that's mentioned in the earlier part of the chapter. So, what is the edit distance problem? You're given two sequences or string of characters. One is length m, the other is length n, and you have to make some number of edits to make them the same. That's the problem, and it could be applied to genome editing or finding a closest matching word or something like that. So there are many applications to this problem, but in this case, the book talks about the example of comparing exponential with polynomial. And just to make sure we are aligned to this understanding, the way it does it is that it puts an empty character on each side, an empty character before the polynomial, empty character before the exponential. And then when you start this, the boundary condition is like this. You write this, the one that is empty versus empty. If you compare that, you put a zero here, right? You start with a zero. That's the starting point. Now, if this is an empty string and you want to compare it to exponential, as you increase the number of characters, you basically, if you have empty versus e, then the distance is one. If you have empty versus ex, the distance is two. So it's trivial to just walk down this and add just plus one or whatever the cost of it was, 1 2 3 4 5 6, and if the whole thing was exponential you get 11 here. And same thing on this side, if this was an empty string, then the cost of comparing empty versus p versus po versus pol, etc., it's trivial to write this down. The only interesting thing is that comparing empty to empty is zero, right? So that's the zero cost comparing empty to empty, and then everything else here is trivial. Okay, so now let's look at how this matrix is actually filled up. This is the minimum cost matrix for the edit or the edit distance. So the way it's filled up is that there are a couple of options. Now this was given to us, this first row and first column, they were given to us. When you start to fill the next, let's say this one. So when you fill this column or this box here, you can come from a couple of locations. Okay, you are here, right? So one possibility is that you can, when you are at the empty point, you have a couple options. You can go this way, okay? You can go this way or you can go this way. What does that mean, right? So if you are at the empty point, which is here, you have not looked at any character on any of the strings, what you can do is you can either skip E, right? You can skip E, so you still, all you have done is you have skipped E. Now you're going to be looking at next, you're going to be looking at X, P, O, etc., etc. That's one thing. If you go straight down this path, you have skipped E. From here, if you go this path, then that means you have skipped P. Okay, you have not looked at E yet, but you have skipped P. Okay, so what's remaining on you is O, L, Y, N, O, M, I, A, L. So this part is remaining, but you have skipped P. And if you go this way, there are two possibilities. One means that if E and P, you basically are taking over both E and P. And if you are taking over E and P, the possibility is that either this E and P were exactly the same, in which case you have taken both and you have basically skipped both because they matched. And then the cost in this direction would have been a zero. But if they mismatch, like in this case, they are mismatched. So one side you have E, the other side you have P. But if you go down this path, you're skipping both strings by one character, right? So you're skipping E and you're skipping P. And that's how you have come here. And that means because E and P are not the same, the cost is one. So again, to reiterate, if you go down, if you go vertically down, that means you're skipping on this string by one character. Okay, you're just skipping this character. If you go in the row, then you're skipping the character on this side. Okay, you're skipping P. But if you go down this, you're skipping both. Now, when you skip both, either the both of them match or they mismatch. If they match, then the cost is zero for that operation, and if they mismatch, the cost is one. Okay, so that's how this matrix is filled up. Now I'm just going to show you an example here. If you are at 0 0, and if you go down this path, you know that E and P are not the same. So if you come from this path, what would be the cost? Because they're mismatched, cost would be 1. If you're coming down from here, this was already 1. And if you come down from here, what would be the cost? If you go down, the cost is plus 1. According to the book, if you come down 1, you're skipping this E, and therefore the cost is 1. If you come from this side, so 1, this was already 1, and 1 plus 1 would be 2. So the cost from coming down from here would be 2. Going from this side, this was already 1. So if you go from here into this, you're skipping P. Okay. If you skip P, the cost is plus 1. So 1 plus 1, 2. So coming from here is 2, coming from here is 2, coming from here is 1. What is the minimum cost of coming from anywhere? It's 1, and it's coming from this direction. This diagonal arrow is the minimum cost. Okay, so that's the basis of how you derive the cost for a given cell. It's the minimum cost coming from the 3 directions, right? You can come from the top by skipping a character on the y-axis. You can come from the left by skipping a character on the x-axis, and you can come from diagonal by skipping a character on both axes. And that's how you get here, and the cost is accordingly computed. Next, Next up, what we can do is we fill up like this, the minimum cost for each box. We fill this all the way to the bottom. And when you have reached the last character of this solution, this cost here is the final cost of, doing the full comparison. And now, there's 2 parts to the problem. First, you have to compute this cost matrix, right? And the cost matrix is only part of the solution. Once you have computed the cost, you can know what is the cost to compute, edit distance between exponential and polynomial. We know the answer is 6. Okay, and if you're asked to compute the actual edit path, then you have to backtrack, and you have to see where this came from. What was the minimum link that came here? And you can see that this link will point here, and this link will point here, this link will point here, this link will point here, this will come from here, because you know which path you took to arrive here, right? You didn't come from here, you didn't come from here, you came from here. And so on and so on. So you can track it back all the way. And once you have filled this whole matrix, you can find this backtrack path. Keep in mind that till you have filled this whole matrix, this path is not visible to you. Okay, this path is only visible once you have filled this whole scoring matrix, and then you can walk backwards from that matrix to find what was the actual path that brought you here. Okay, and that's how you basically derive the cost. Now, the first part of the problem is actually asking us um, that, if we were to not do this backtracking, right? If we were only asked to compute the edit distance, um, then order n space is enough, right? If you are not required to find this arrow path here, right? If no arrow path is required, what is the space complexity of this problem? Now, we show here we have stored everything, right? We stored the full matrix. And therefore, obviously, if this was m and this was n, then this is order m in space. So we have consumed order m in space here. But the question is asking, if you only had to compute the 6, this edit distance, could you do it better? And the answer is yes, you can do better. The way you do it better is you realize that to compute this column, right? If you want to compute this column, you don't need this full matrix. All you need is the previous column, right? You knew this column, and using this column and part of this second column, you computed the rest of the column, right? So the way this breaks down is that you really, at any given point in time, you only have 2 columns that you work with, and the space needed is 2 columns worth. So this was a column is really of the order m or n, whichever is the worst. So we can assume that n is the worst, and therefore the complexity here was really like 2 times n, therefore it's order n. So the space complexity for just filling this matrix all the way to this point was order n, clearly. Okay, because at any given point in time, all you need to store to compute and fill up this column is the previous column and probably part of this because you come from either left top or the diagonal. So you only keep two columns, and then once you have filled this column, you empty this out and put it in the front of it, and you start filling it again, and then you throw this away, and then you put the so you keep doing that. You keep throwing away the previous column, and then you have this column remaining using this column, and part of this you basically compute this one. Okay, so that's that's the first part of the solution, and this is where we will stop. Next time, we'll pick up right from here to describe how this algorithm can be actually modified to using this linear space also compute this arrow path, right? This arrow path is actually possible. And the whole point of this problem is to show that if we did not have, when you start dealing with not just comparing exponential with polynomial, but when you start comparing genomes, etc., this space could be massive. It could take massive amounts of memory to store the whole sequence on the left, the whole sequence on the right, and a full matrix of computation. So the way this is organized is that can we find a space efficient algorithm? And so that's going to be the next section of this video. We'll walk through that next. And hopefully you enjoyed this video and liked it. Mostly it was just a recap of how edit distance works, but we introduced the first problem in this episode. And so, if you liked it, give us a thumbs up and subscribe if you really enjoy dynamic programming and the solution series that we are bringing to you. And we'll be back with more. And until then, thank you and see you later. Bye.